Hello and welcome to another Python interview practice problem. This one is based on Conway's Game of Life, which is near and dear to my heart because I a few years back I was getting really into a book by Stephen Wolfram called A New Kind of Science, where he talked about all kinds of fractal images and cool patterns that could be made with cellular automata like this. I very much enjoy recreational mathematics, and because it can make some really cool stuff and visually um, show how powerful even the most simple algorithms can be. And this is one of them. So basically, what we're doing is we have a grid of cells, and based on what the neighbors of the cells are, if they're alive or dead, will determine if the cell will be alive in the next iteration. So for example here, any live cell with fewer than 2 live neighbors dies if caused by underpopulation. So here, for example, this cell only has 1 live neighbor, right? So it dies in the next iteration. Any cell with 2 or 3 live neighbors lives on in the next generation. So if you have a live cell and it has 2 or 3, this one's got 2, 1, 2, and it lives on in the next generation. Any live cell with more than 3 neighbors dies, as if by overpopulation. I can't see an example of that here, but we will implement that. Any dead cell with exactly 3 live neighbors becomes a live cell. So you see that here, this is a dead cell, but it's got 3 live neighbors. So neighbors are up, down, left, right, or diagonal, directly adjacent. So we need to keep the old board. So what we're doing is we're editing the board in place, but we need a copy of the original board because we need to make these adjustments to the board based off of the original starting position, right? So one way we can do that is we say we'll make a copy of the board. We'll call it copy, and then we'll make a list of rows, and then we will copy every row in the board. So we'll go row, and we'll use list splicing, like we did in the other video, to copy the entire row from beginning to end. And then we're going to say we're going to do that for row in board. So that will populate this list with copies of the rows, and we'll have our original board. So then we want to make a variable to hold on to how many live neighbors we currently have. And I'm doing this because I don't want to do it inside of a scope, inside of a more limited scope. I would rather have it just be defined here, and instead of creating and destroying the variable. So live neighbors is going to be 0. Alive is going to be a Boolean, and we're going to call that false by default. And then we're going to say for I in range length of the copy. So this is going to iterate through the rows. And it's going to give us the index of the rows as it iterates through them. and we'll say for j in range length of copy the length of the first row. The length of all the rows are going to be the same, but we're going to just pick the first one, and this is going to iterate through the columns. So every time we get to so this is going to go through each row, and within each row is going to go through each column. And so now this will look at each individual cell. So every time we look at a new cell, we want to say alive equals false by default. And we're going to say live neighbors equals 0 by default. And then we'll check if it's alive. We'll say if copy I, if the row I in the column J, if it's a 1, then we're going to say alive equals true. Because if it's a 0, that will evaluate to false. But if it's a 1, it will satisfy the if condition. So now, within the iterating through the rows and columns, we're going to do this again, but just for the 3x3 block of neighbors, or the 8 neighbors. But we'll check the occupied space, or the cell. We'll check the cell that we're looking at as well, but we will just factor that out of the solution. So we're going to go for A, and this time we're going to go let's see it, show you it doesn't really matter which way you do it. We're going to go look at the columns. For each column, we're going to iterate through the rows. And right here, I use a pretty cool trick that I saw elegantly written in a book I'm reading right now. It's called Coding the Matrix, Linear Algebra Through Computer Science Applications. I remembered it because it was so elegant in the way it was written, and it was used for a different algorithm for some other kind of problem, but it did this neighbor checking thing. And the way it did it was like this, because you need to not check cells off of the board, right? Like you can't check like row -1 or column -1, right? So you will check the range, in the range we're looking in, we'll check from the maximum value 0 or j minus 1, whichever is bigger, right? So if it's if j minus 1 is less than 0, then we're going to just start it. We're just going to cut it at 0 and start from 0, right? And then minimum, what is bigger, or what is smaller, j plus 2 or length copy it at 0. So So we're going to check what is if we also so notice it's j plus 2 because the range is exclusive, so we don't include the last element, and that's why we have length copy, which is an index further than we actually have. So then this is going to check if we have the alive neighbors in the columns, and then we're going to do it for the rows. All right. So we're going to check each of those cells in that 3x3 square, and we're going to say if copy at L for the row and K for the column, we're going to add to live neighbors. And then after we go through that, we're going to check if our cell is alive, the one in the middle. And if it is, we're going to subtract that off because we don't want to count that one. So now that we've done all of that, we can look at the conditions, and we can implement all these conditions. So depending on how many live neighbors we have and whether or not the cell is alive, we'll be able to evaluate these 4 conditions. So first we'll say if alive and live neighbors is less than 2, then we're going to say board at ij we're going to, if there's not, if there's less than 2 neighbors, it's going to die from underpopulation, right? And we'll say else if alive and live neighbors is less than or equal to 3, because we already checked that it's not less than 2, right? If it's 2 or 3, then, and it's already alive, it just stays alive because it's populated enough. So live and live neighbors less than or equal to 3. And then we're going to say board ij equals 1. We'll say elif alive and live neighbors is greater than 3, then it's going to die from overpopulation, right? Board ij equals 0. And then finally, the final condition, elif not alive and live neighbors is exactly equal to 3, in which case we want to make that space now alive. Right. And let's see if that works for us. And object is not iterable. What did I do here? Oh. That should be that, like that. Okay, try that again. And there we go. Thank you very much for watching, and I'll see y'all next time.